In this presentation, I will introduce the theory of learning from different domains, known as domain adaptation. Domain adaptation occurs when the training data and testing data come from different domains. This is a very common situation in real-world machine learning applications. Let's start with some examples to illustrate domain adaptation. For example, in the case of self-driving cars, your vision module might be trained on street view data from a country where cars drive on the right side of the road. However, if you plan to deploy the vision module in a country where cars drive on the left side, the distribution of street view images will differ from the training data. Another common case is when a model is trained on synthetic data generated by simulators or other models. This synthetic data often does not exactly match the real-world environment. Therefore, understanding the theory behind domain adaptation is crucial. Now, let's outline the presentation. First, I will introduce the concept of generalization bounds, specifically for cases where the training and testing data are from the same distribution. This means that both the training and testing data belong to the same domain. Then, we will discuss the problem that arises when the training and testing data come from different distributions. In this case, the model may struggle to generalize its learning from the training data. This is the core issue in domain adaptation. Next, we'll explore the causes of domain adaptation problems. We will present a generalization bound specifically for domain adaptation, which helps explain why testing errors may be higher in such scenarios. Finally, we will showcase a real-world application that attempts to alleviate the domain adaptation problem. Let's now dive into the details of generalization bounds in a single domain. First, consider a given dataset. To train a model, a finite number of instances are sampled from this dataset. Initially, a hypothesis H is evaluated on these instances. Typically, this hypothesis does not perfectly predict all training samples, leading to some error. This error is referred to as the training error, denoted as epsilon hat. To reduce this error, the training algorithm adjusts the hypothesis based on the features of the training data. However, the algorithm only sees the training data, not the entire data distribution. To assess how well the adjusted hypothesis performs on the full dataset, another sample, called the testing data, is drawn from the same dataset. The adjusted hypothesis is then evaluated on this testing data, and the error is denoted as epsilon h. The question is, can we achieve low testing error by reducing training error? Can the algorithm choose a hypothesis that generalizes well across the entire data distribution? When learning is successful, reducing the training error epsilon hat can also reduce the testing error epsilon. To ensure this, we need to establish that the testing error can be upper bounded by the training error plus some additional terms. This is the essence of generalization bounds. It can be shown that, with a high probability, typically 1 minus delta, the following inequality holds. Delta is usually small, meaning this probability is high. On the left-hand side, we have the testing error epsilon, and on the right-hand side, we have the training error epsilon hat, plus an additional term. This inequality indicates that, with some probability, the testing error is bounded by the training error plus a generalization gap. The generalization gap term includes n in the denominator, where n is the number of training samples. The more training samples there are, the smaller the generalization gap becomes. When the generalization gap is small, a small training error implies a small testing error with high probability. This explains why increasing the amount of training data leads to better generalization. However, this generalization bound does not apply when the training and testing data come from different distributions. Let's look at a common example. Suppose an OCR model for recognizing digits is trained on the MNIST dataset, which only contains black background and white digits. If we then apply this model in a new environment with grayscale digits, we cannot guarantee that increasing the number of black and white training samples will reduce the generalization gap. This is the challenge of domain adaptation. Let's now discuss the causes of domain adaptation in more detail. There are datasets from two domains, the source domain and the target domain. The source domain refers to the distribution of the training data, while the target domain refers to the distribution of the testing data when the model is deployed. To formalize the generalization bound in the target domain, we sample another testing dataset from the source domain. This gives us three types of errors: the training error in the source domain, denoted by epsilon hat s, the testing error in the source domain, denoted by epsilon s, and the testing error in the target domain, denoted by epsilon t. When considering the gap between epsilon hat s and epsilon s, we only need the generalization bound for a single domain. However, there remains a gap between epsilon s and epsilon t, which must be taken into account in the generalization bound for domain adaptation. The generalization bound for domain adaptation was proposed by Ben-David Shai et al. In 2010. In this work, a generalization bound for domain adaptation was introduced. This bound includes two additional terms. The first term measures the distance between the features of the source domain, ds, and the target domain, dt. The second term measures the distance between the labeling functions of the source domain, fs, and the target domain, ft. Now let's take a closer look at the first term, which is the distance between ds and dt. To illustrate this, let's consider some examples. Suppose we have one source domain and two target domains. The source domain, ds, is the MNIST dataset. The first target domain, dt1, consists of white digits on a black background, but with digits that are thicker than those in MNIST. The second target domain, dt2, consists of digits with various grayscale brightness levels and backgrounds. It is clear that the distance between ds and dt1 is much smaller than the distance between ds and dt2. However, the challenge lies in determining how we can quantify this kind of distance. Next, we show the equation used to quantify the distance between ds and dt, and this distance is denoted as d1. We explain the meaning of this equation with the following diagram. The x-axis represents the probability space, denoted by calligraphy B. This probability space is the feature space of all possible data instances. The green line represents the probability density function of ds over this feature space. If certain areas under the green line are large, it means the source dataset contains a higher proportion of instances in those areas. The purple line represents the probability density function of dt over the same feature space. If there is significant overlap between the areas under the green and purple lines, it indicates that the source and target data share many samples with similar features in those regions. Conversely, if the area under the green line but above the purple line is large, it means that there are many features present in ds that are uncommon in dt. By measuring the area where the green line is above the purple line, we can quantify the distance between ds and dt. In this probability space, we select the set B, which is the union of B1 and B2. In this set, the green line is above the purple line. We sum the area under the green line but above the purple line, which we refer to as the green shaded area. This area represents the difference between the probability density functions of ds and dt summed within the set B. It can be shown that d1, the distance between ds and dt, is equal to the sum of the green shaded area and the purple shaded area. Since these two areas are equal, the distance is twice the green shaded area. This is how we measure the feature difference between ds and dt. Now, let's explore how to measure the difference between the labeling functions in the source and target domains. We provide three examples of labeling differences in the digit recognition problem. In this case, we assume there are only 5 types of digit images, ranging from digits 1 to 5. In the first case, the labeling function in the source domain fs labels odd numbers as 1 and all others as 0. In the second case, the labeling function in the first target domain ft1 labels the digit 1 and prime numbers as 1, while others are labeled as 0. In the third case, the labeling function in the second target domain ft2 labels numbers with an integer square root as 1 and the rest as 0. The numbers with labels different from those in the source domain are highlighted in red. It is clear that the distance between fs and ft1 is much smaller than the distance between fs and ft2. However, the question remains, how can we quantify the distance between fs and ft? The distance function d2 is used to quantify the distance between fs and ft. Here, we provide examples to illustrate how this function works. In the first example, the labeling function in the source domain labels odd numbers as 1. The labeling function in the target domain labels the number 1 and other prime numbers as 1. The numbers with labels different from the source domain are highlighted in red. The distance function d2 counts the number of labels highlighted in red in the target domain and divides this by the total number of labels. In this case, only one label is highlighted in red, resulting in a distance of 0.2. In another example, the labeling function in the target domain labels numbers with integer square roots as 1. The distance function d2 performs the same operations. Here, 4 labels are highlighted in red, resulting in a distance of 0.8, which is greater than the 0.2 in the previous example. This explains how the distance between labeling functions is quantified. Finally, we present a real-world application that demonstrates how to reduce the distance between features and labeling functions. This application is from the work of Shrivastava Ashish et al. 2016. It shows how to generate synthetic data to train a model. In this example, the source domain is the distribution of synthetic images, and the target domain is the distribution of real images. These synthetic images are used to train a model to estimate the angle of eye gaze. The synthetic images are generated by a simulator. Given a specific eye gaze angle, these images depict human eyes looking in that direction. However, since these images are created using a 3D framework, and lighting is simulated using physical laws, the feature distribution of these images differs from that of real images. If the model is trained on these synthetic images, there will be a large feature distance when it is tested on real images. To address this, a generative adversarial network, GAN, with a refiner and discriminator D, is used to refine the synthetic images. This refiner reduces the distance between the source and target features. However, the goal of using synthetic data is to reduce the labeling effort for real images. The real images used to train the GAN do not have labels related to eye gaze angles. If the GAN is trained on these unlabeled real images, it may not generate refined images with precise eye gaze angles. As a result, the eyes in the refined images may not be looking in the same direction as in the original synthetic images. This leads to a larger difference between the labeling functions in the refined images and the original synthetic images. To minimize the difference in labeling functions, a loss function is applied to constrain the pixel difference between the synthetic and real images. This function reduces the distance between the source labeling function and the target labeling function. When the eye gaze angle differs between the refined and original synthetic images, the pixel difference will be larger. Therefore, constraining pixel differences helps ensure that the labeling functions of the refined and original images remain similar. Here are the results. The top row shows the original synthetic images, which look somewhat artificial. In contrast, the bottom row shows the refined images, which appear more realistic. Additionally, the eye gaze angles in the top and bottom rows are consistent. This indicates that the distance between the labeling functions of the top and bottom images is small. In the right figure, the performance of models trained on synthetic and refined images is shown. The x-axis represents the difference between the predicted and actual eye gaze angles in degrees. The y-axis shows the percentage of images where the predicted angle deviates from the actual angle by a certain degree. A curve closer to the upper left corner indicates better model performance. The red dotted line represents the performance of the model trained on the original synthetic data, which has the lowest curve. This is due to the large difference between the features in the source and target domains. The solid red line represents the performance of the model trained on 4 times more synthetic data. This only slightly improves performance, since increasing the number of samples reduces the generalization gap within the same domain, but does not reduce the gap between different domains. The blue dotted line shows the performance of the model trained on refined synthetic data. This model performs better because the generalization gap between the source and target domains is reduced. In this case, generating more training samples is effective because the training and testing data are from similar distributions. Increasing the number of samples further reduces the generalization gap in the source domain, as shown by the solid blue line. This example demonstrates how generating synthetic data can improve model performance when domain adaptation is taken into account. Now, let's summarize the key takeaways from this presentation. The first point is that domain adaptation occurs when the distribution of training data differs from the distribution of testing data. This phenomenon is common in real-world applications and deserves careful consideration. If you're unaware that your training and testing distributions differ, collecting or synthesizing more training data may not be effective. When domain adaptation occurs, the generalization gap between the two domains is caused by differences in features and labeling functions. There is a distance between the source feature distribution, ds, and the target feature distribution, dt. Similarly, there is a distance between the source labeling function, fs, and the target labeling function, ft. To improve the performance of models trained on synthetic data, it's important to focus on reducing these distances. For example, using a generative adversarial network to make synthetic data more realistic can help. However, it's also important to design an additional function to ensure the labels remain consistent between the original and refined synthetic data. Finally, here are some references for further reading. The first is the work of Ben David, Shai et al., which provides the theoretical foundation for generalization bounds in domain adaptation. The second is the work of Shrivastava, Ashish et al., which demonstrates the application of generating synthetic data using domain adaptation techniques. This concludes the presentation. Thank you for listening.